Welcome to Learning AI Keywords Fast Track, CNN. Today, we'll explore how artificial intelligence can see not with eyes, but with smart algorithms called convolutional neural networks. Have you ever wondered how your phone recognizes your face or how self-driving cars spot pedestrians? The answer lies in CNNs. In this session, you'll discover how these systems work using simple ideas, fun analogies, and real-life examples. No prior experience needed, just curiosity. We'll start from the basics and build up step by step so you can truly understand how machines make sense of images. Let's dive in and unlock the world of computer vision together. Let's take a quick look at what's coming up in this session. First, we'll introduce CNNs and explain why they're such a big deal in artificial intelligence. Then we'll dive into the core building blocks, what makes a CNN tick. After that, we'll walk through exactly how a CNN processes an image step by step, using easy-to-follow visuals. Then we'll explore real-world applications, like medical imaging and autonomous vehicles, so you can see how this tech changes lives. Finally, we'll wrap up with a summary, some fun practice activities, and tips for going further. This roadmap ensures you build knowledge gradually, from simple ideas to practical understanding, all in plain language. By the end, you'll not only get how CNNs work, but also feel confident explaining it to others. Ready to begin the journey? So why are CNNs such a breakthrough in AI? Well, imagine trying to describe a photo to someone by listing millions of color numbers, one for each pixel. That's how regular neural networks see images, as a long string of data with no structure. But humans don't see that way. We notice shapes, edges, and familiar objects. CNNs were designed to bridge that gap. They process images in layers, starting with basic features like lines and curves, then combining those into more complex structures like wheels or eyes. This mimics how our brains work when we look at pictures. For example, if you glance at a dog, you don't scan every pixel. You instantly recognize floppy ears or a wagging tail. CNNs do something similar by focusing on local patterns instead of raw data. Because of this smart design, they excel at tasks like identifying faces, reading handwriting, or spotting tumors in medical scans. Simply put, CNNs give machines a smarter way to see, not perfectly like humans, but effectively enough to power many of today's coolest technologies. Now let's understand what a convolutional neural network, or CNN, is in simple terms. At its core, a CNN is a type of artificial intelligence specially designed to make sense of images. While traditional models need humans to say things like look for two round shapes for eyes, CNNs figure that out themselves. They learn directly from examples. Imagine showing a CNN thousands of cat photos labeled cat and dog photos labeled dog. Over time, it starts noticing recurring patterns like pointy ears or whiskers that help it tell the difference. This ability to automatically detect relevant features is what makes CNNs so powerful. Think of it like a team of art critics looking at a painting. The first critic examines brushstrokes and colors. The second starts seeing shapes, maybe a tree or a mountain. The third puts it all together and says, this is a landscape. Each level builds on the last. That's exactly how a CNN works, layer by layer, turning pixels into understanding. And the best part? You don't need to program every rule. The network learns through experience, just like a person would with enough practice. Let's break down the three main layers that make up every CNN. First, there's the convolutional layer. This is where the magic begins. It scans the image using small filters. Think of them like tiny magnifying glasses that slide across the picture looking for specific patterns, such as vertical lines or sharp corners. Each filter highlights different features, creating feature maps that show where those patterns appear. Next comes the pooling layer. Its job is to simplify the data. Imagine taking a detailed map and zooming out to see only the major cities. That's what pooling does. It keeps the most important signals while reducing size, which speeds up processing and prevents overload. The most common type is max pooling, which picks the strongest value in each block. Finally, after several rounds of convolution and pooling, we reach the fully connected layer. This is where the network makes its final call. It takes all the condensed information and uses it to answer, is this a cat, a dog, or something else? Just like tasting a sandwich tells you whether you like it, this layer combines everything to give a prediction. Together, these three layers form a smart pipeline that turns chaos into clarity 1 pixel at a time. Let's follow an image as it travels through a CNN. It all starts with input, the image itself, broken down into a grid of pixel values. Each pixel is just a number representing brightness or color. Now, enter the first convolutional layer. Here, small filters, also made of numbers, slide across the image, multiplying and adding values to produce feature maps. One filter might light up wherever it sees a vertical edge. Another responds to horizontal lines, but not all signals are useful. That's where ReLU comes in, a simple rule that turns off any negative results, like muting background noise so only strong patterns remain. Next, the pooling layer steps in. It divides the feature map into small blocks and keeps only the highest value from each. This is max pooling. The result? A smaller, cleaner version of the data that still holds the key details. And guess what? This whole process repeats. Another convolution layer might now detect combinations of edges like corners or curves. More pooling shrinks it again. With each cycle, the network moves from simple features to complex ones. Eventually, after several layers, the rich distilled data reaches the fully connected layer. This final stage weighs all the evidence and gives us the answer, yes, this is a face, or that's a stop sign. It's a journey from pixels to meaning, and it happens in milliseconds. One of the trickiest ideas in CNNs is the concept of filters. So let's make it crystal clear. A filter isn't a camera lens or an eye. It's a tiny grid of numbers, usually 3 by 3 or 5 by 5 in size. Think of it like a stencil or a cookie cutter. As it slides over the image, it performs math operations to check how closely the underlying pixels match its pattern. For example, one filter might be tuned to detect vertical lines. When it passes over a part of the image with a strong vertical edge, like the side of a building, it outputs a high number. If there's no match, it outputs low or 0. Another filter might look for horizontal lines, diagonals, or blobs. And here's the cool part. The network uses many filters at once, so it can catch all kinds of features in parallel. Over time, through training, these filters become better at spotting what matters. It's not unlike how you'd find a friend in a crowd by scanning for familiar features, say glasses and curly hair. You're not seeing everything at once. You're matching patterns. That's exactly what CNN filters do mathematically, efficiently, and automatically. No programming required. The network learns which patterns are useful all on its own. You might think CNNs are futuristic lab experiments, but you interact with them every day. Let's look at 3 real-world uses. First, in medicine. Hospitals use CNNs to analyze X-rays and MRI scans. These networks can spot tiny tumors or abnormalities faster than a human doctor might, giving patients earlier diagnoses and better outcomes. It's not about replacing doctors. It's about helping them focus on what matters. Second, in self-driving cars, autonomous vehicles have cameras all around, feeding live video into CNNs that constantly scan for pedestrians, traffic lights, and other vehicles. When a child runs into the street, the CNN detects them instantly and tells the car to stop, saving lives through split-second decisions. Third, on social media, ever upload a photo and see suggested tags for your friends? That's a CNN at work. It recognizes faces across different lighting and angles, making sharing easier and more personal. Beyond these, CNNs power retail apps that let you take a picture to find similar clothes, security systems that monitor surveillance footage, and even agriculture tools that assess crop health from drone images. The impact is huge and growing. Let's clear up some common misconceptions about CNNs. First, many people think CNNs work exactly like the human eye. But that's not true. While they're inspired by biological vision, CNNs don't have retinas or optic nerves. Instead, they use pure mathematics, filters, matrices, and activation functions to detect patterns. They simulate aspects of sight, but they don't see the way we do. Think of them as pattern detectors, not digital eyes. Think of them as pattern detectors, not digital eyes. Not digital eyes. Not digital. Second, there's a belief that more layers always mean better performance, but deeper isn't always better. Too many layers can cause overfitting, where the model becomes too specialized on training data and fails on new images. It's like memorizing answers for a test, but failing when asked a slightly different question. A good CNN balances complexity with purpose. Third, some assume you must code to understand CNNs. Not at all. You can grasp the core ideas like layers, filters, and pooling without writing a single line of code. Focus on concepts first. Use metaphors, sketches, and examples. Once you understand the why, the how becomes much easier. These clarifications help you avoid pitfalls and build accurate mental models from the start. Let's review the key points you've learned today. First, CNNs are a special type of AI built specifically for understanding images. Unlike regular models, they analyze spatial patterns, edges, shapes, textures in a way that mimics human perception. Second, every CNN has 3 essential layers. The convolutional layer finds features like lines and corners. The pooling layer simplifies the data while keeping key info. And the fully connected layer makes the final decision, like saying this is a dog. Third, CNNs learn automatically. You don't need to program rules. They discover important patterns through exposure to labeled images. Fourth, they're already everywhere, spotting tumors in hospitals, guiding self-driving cars, and tagging your friends on social media. And finally, you don't need to code to understand them. Start with concepts. Use analogies like art critics or sandwiches and sketch diagrams. Mastering these ideas gives you a solid foundation for future learning, whether you want to dive into deep learning, build AIOps, or just stay informed in a tech-driven world. If you can explain CNNs in your own words now, you've succeeded. Time to put your knowledge into action. Let's do a few quick exercises to reinforce what you've learned. First, grab a pen and paper or open a Notes app and draw a simple CNN pipeline. Start with an input image, then draw arrows through a convolutional layer, a pooling layer, and finally, the fully connected layer. Label each part with its role. For example, finds edges under convolution, reduces size under pooling, and makes decision at the end. Don't worry about perfection. This is about understanding flow. Next, try answering these questions. What does ReLU do in a CNN? Why is pooling important after convolution? And how does a CNN differ from a regular neural network when handling images? Take a moment to think or say your answers out loud. Finally, imagine a new scenario. A delivery robot using a CNN to sort packages. Which layer would first detect barcodes? Hint: early layers find simple patterns like lines and grids. These exercises help move knowledge from your head into lasting memory. If you stumbled on anything, that's okay. Go back and rewatch that section. Learning is a process, not a race. Let's pause for a quick self-assessment. Ask yourself, can I explain what a CNN is without looking at notes? Can I name at least 2 real-world applications like medical imaging or facial recognition? Do I clearly understand the difference between the convolutional layer, which detects features like edges, and the pooling layer, which reduces data size. And finally, could I sketch a simple CNN diagram showing how information flows from input to output? If you can confidently say yes to all four, congratulations, you've mastered the fundamentals. If you hesitated on any, that's perfectly fine. Go back and review the relevant slide. Maybe re-listen to the explanation or redraw the diagram. Understanding builds over time, especially with spaced repetition. Try revisiting this checklist in 1 day, then again in 3 days. Each review will strengthen your recall. Remember, the goal isn't perfection, it's progress. And you're doing great so far. You've built a strong foundation. Now, where can you go from here? If you're excited to go deeper, there are several natural next steps. First, you can start training CNNs yourself using beginner-friendly datasets like CIFA-10, which contains small images of animals, vehicles, and objects. With tools like Google Colab and TensorFlow, you can run experiments in your browser. No setup needed. Second, explore transfer learning. This powerful technique lets you use existing CNNs like VGG or ResNet that were already trained on millions of images. You can then fine-tune them for your own task, like identifying plant diseases or sorting artwork by style. It's like borrowing a smart assistant who already knows a lot and just needs a little guidance. Third, deepen your knowledge in related areas. Study basic neural networks to understand how learning works under the hood, or dive into image processing to learn about color channels, resizing, and noise reduction. All of these skills complement your CNN knowledge and open doors to real projects. The AI world is vast, but you now have the map to navigate it. Congratulations, you've completed the A Keywords Fast Track on CNNs. Take a moment to appreciate what you've learned. You now understand how machines can see using convolutional neural networks. You know the 3 key layers, how data flows through them, and where CNNs are used in real life. You've cleared up common misconceptions and even practiced explaining these ideas in your own words. That's no small feat. Whether you're preparing for a career in tech, building a project, or just satisfying your curiosity, this knowledge gives you an edge. And the best part? You did it without needing advanced math or coding. From here, you can choose your path, dive into hands-on labs, explore more AI keywords, or teach someone else what you've learned. Remember, every expert was once a beginner. You've taken a big step forward today. Keep asking questions, stay curious, and never stop learning. Thank you for joining this session, and welcome to the world of artificial intelligence. To keep growing your AI skills, here are some excellent next steps. First, try the CNN Explicable, an interactive website that shows how a CNN processes images in real time. You can see filters lighting up, feature maps forming, and decisions being made. It's a fantastic way to visualize everything we've covered. Second, check out beginner-friendly online courses. Platforms like Coursera, edX, and Khan Academy offer introductory AI classes with visual explanations and gentle pacing. Third, join a learning community. Reddit's Learn McKinney is a supportive space where beginners ask questions and share progress. Finally, create a set of flashcards with terms like convolutional layer, pooling, and ReLU. Review them daily for a week, then weekly. Spaced repetition turns short-term learning into long-term mastery. And remember, you don't have to do it all at once. Pick one resource, spend 10 minutes exploring, and build from there. Every expert started exactly where you are now with curiosity and a willingness to learn. Keep going, you've got this.